All right. This is actually energy. This is energy and momentum. But you want to know something funny? I discovered when I started this unit in class that the initials are actually E and M. So this is E and M, but not to be confused with E and M, because E and M is actually electricity and magnetism, but it's also energy and momentum, right? So it gets kind of confusing there, at least in terms of names and stuff. But you're going to hear me, and the only reason I would ever refer to both as E and M is that only to confuse you, really, and that's why I do it. Okay, we're going to start by talking about some basic energy concepts that we went over in Physics 1. First off, starting with the equation for work. Okay, you learned this equation in Physics 1. Its work is equal to F d cosine theta. Okay, you might also see that it's like fx cosine theta sometimes. And theta, really quickly, is the angle between force and distance, okay? And it's important to note that work is a transfer, okay? Work is a transfer, okay, of energy, okay, from one object to another, okay? Or it could also go from one, I guess I should say here, form. Okay, so you can turn energy from like potential into kinetic, or you can transfer energy from one object into another in something like maybe like a collision. Okay, the units of energy are called joules. Okay, and that is represented with a capital J. Okay, um, oh man, I'm so sad. I wrote this in my key in green, but it actually my green pen recently just died out on me. The kinetic energy equation, this is from Physics 1, is K equals 1/2 mv squared. Okay. Gravitational potential energy is U sub g. Remember, we use U instead of like P for potential energy. Okay. U sub g is equal to mgy. Okay. What about force applied by a spring? It seems kind of random to have this question in here. Okay. The force applied by a spring is simply, you call this Hooke's law, right? K times X. Okay. And you typically will see that there's like a negative before the KX. And that's just to show that it's like a restoring force. Okay. So that, it opposes what's being done to the spring. Okay. And you should hopefully remember that K is equal to the spring constant. Okay, and X is the spring stretch, okay, or compress. Okay, so that's going to be for that right there. Now, don't get confused, right? There's K, and then there's also K. This should be lowercase k. This is uppercase K. All right. Okay. Okay. Um, Spring potential energy, okay, is U sub s. It's very similar, but not quite. 1/2 kx squared. You actually might be able to notice that there is a relationship here for if you're thinking with your calculus brain, okay? If you got your calculus thinking cap on, then you probably are recognizing a pattern there between the two, okay? You can lose energy to friction, and I'm going to call this E lost, okay? So to dissipate energy, you need to have friction, okay? And it can only be lost when kinetic friction is acting. It doesn't make sense for static friction to dissipate any energy because you're not moving, right? You're not causing any transfer because you're not moving, right? Static friction, you're not even moving, right? Mechanical energy is the sum, okay, sum of kinetic energy, okay, and potential energy, okay. The law of conservation of energy states that in a closed system, total energy remains constant. In a closed system, okay, total energy remains constant. Okay. Um, the conservation of energy equation simply states that, again, whatever energy you start out with needs to be the same as whatever energy you end with. So what we can say is that any kinetic energy we initially have plus any potential energy we initially have plus any plus okay, any energy that we gain along the way, okay, needs to be equal to the final amount of kinetic energy plus the final amount of potential energy plus whatever energy we lose along the way. Okay? So, right, everything should balance out in the end of the day. Okay? I saw a little like gnat. Okay, I thought I was going to be able to get it. Okay, I mean it would suck if I did because I have to go wash my hands and cut the video like short. Conservation of energy is used should be used when when you need to relate speed to position, and you're going to see why that's important later. Okay, you should use Newton's laws when you're solving. Okay, for specific force or for acceleration. So very important to note when you need to be using these two principles. Okay. Okay. And then power is the final thing that to review here. Okay. Power is simply it has two major definitions. It's the rate at which, okay, two different ways to define it. Either work is done, okay, or energy is used, okay. The units for power, in case you don't remember, the units for power are called watts, okay, which is a joule per second, okay. And then power, the formula for power is work over the change in time. So work done over a period of time. Or you can also see it's the change in energy over the change in time. And again, if you're thinking with your calculus cap on, then you probably can rewrite this as a different relationship using calculus, okay? Okay, well that's a brief intro to energy and a brief review of it. Okay, have fun.